això. Okay, so good morning, everybody. Today we will, Albert Jimenez will review this paper called Deep Image Retrieval Learning Global Representations for Image Search. That's a paper from Albert Gordo, Jon Almazan, Jerome Revaud, and Diane Larlus from Xerox, I think, yeah. Right? So, Albert, thank you very much for preparing the paper, and the floor is yours.
Thank you, Xavi. Well, as Xavi said, I will review that paper from the people from Xerox. Here you have the arXiv link, and they said that they will release the code, but it's not yet released. So let's start introducing the retrieval task. Well, as I have said before, you have an image query, and you want to search in a database of images, the most similar ones, and give a ranking of images ordered by similarity with the query. Well, the related work, most of the work that has been done before is based on CNN-based retrieval. That is, CNNs trained only for the classification task, and then they use these networks for the retrieval tasks, or they fine-tune with another dataset of retrieval, and then, but only with the classes information and a classification loss. So the features they get are very robust to intra-class variability, and as we want to find similar images between the same class, this information is not very good to us. And also the lack of robustness to scaling, cropping, and image clutter. So we are interested in distinguishing between particular objects from the same class, and there are different function losses to train the networks as triplet loss that it's better for solving this problem. Well, another related work that is the main related work to these authors, well, to this paper. The authors of the paper inspired a lot in this work called, well, particular object retrieval with integral max polyfill of CNN activation. And in this paper by Tolias et al., they propose to use regional maximum activation of convolutions, and I will explain it now. What they do, they have an image and a convolutional neural network, and they go to the last layer of that convolutional network, and for each feature map, well, they have a grid of different scale regions, and for each region they compute a feature vector that is formed by the maximum activation of each feature map for each region each time. And then they normalize them. They do a PCA to reduce the dimensionality to a fixed length. They normalize and they sum all the feature vectors for each region. And then they can compare images and code this way, just using the dot product, and it's very efficient and fast. Well, I will explain now the contributions of this paper. The first one is that they use a stream Siamese network. A Siamese network means that this convolutional neural network and the PCA that is implemented as a shift plus a fully connected layer share the weights between the three networks. And finally, they optimize the weights using a triplet loss function that is very used for retrieval tasks and for similarity. So here, as inputs, as they are training by triplets, they have the query image, a relevant image, and then a non-relevant image. And this is the loss function. As I have said before, this is the query, the relevant and the non-relevant, and they have a threshold that is m to control the margin, and these are the distances computed as the dot product of the descriptors. So the second contribution that they do is in the RMAC, as I have said before, they use a read grid. And here in this paper, they propose to use a region proposal network. That is, well, I will explain later what it is. But they want to find regions of interest, and that means where the objects are more probably to be located, the objects of interest. And well, they do a scheme similar to the guys of faster CNN. And here you have a link if you want to know more to the arXiv paper and also to an Amaya presentation of this CV. And region proposal network want to predict for a set of bounding boxes of different scales and sizes at all possible image locations, a score predicting how likely is an object of interest to be. And also, at the same time, they perform regression to improve the location of each bounding box. This is the big loss function, but it's well explained in her slides. If you want to know more. And then, as a summary, they propose an architecture that is able to encode one image in a forward pass in an efficient way. And images can be compared very fast using the dot product. And well, at this time, it's very fast. Let's see the experiments they did. Well, first of all, they do the training in the landmarks dataset, and they do testing in Oxford, Paris, and in Ria holidays. Well, they propose two different datasets to test, well, to train, sorry. The first one is the landmarks, but with all the images from Oxford and Paris removed. And the second one, they propose a cleaning of the landmarks dataset. Well, to do that cleaning, they do the shift and adhesion-affine K-point detection, and they construct graphs of similar images, and they discard the images that are on the edges and that ones that are not well connected to the others. So they finally reduce a lot the number of images they use. Also, to train the region proposal networks, they need a ground truth for the landmark datasets. They don't have it, so they propose a method to automatically estimate where the objects of interest are in this dataset. So they define a bounding box estimation method first, as they have computed with the shift all the key points. They define an initial bounding box as the minimum rectangle that encloses all that matched key points, and then for the pairs in the graphs that I have explained before, they predict the bounding box doing transformation between the images, and then they update with some weights, and then they do a merge, and they iterate this until they get like a better position for the bounding box with all the images information. And here you can see an example of the initial versus the final estimation of the bounding box. So it works very well. Then the experimental details. They use the BGG network pre-trained on ImageNet. They fine-tune with the landmarks dataset. And about the triplets, they say that they select them in an efficient manner. They first do forward pass to obtain the image representations, and then they select the hard negatives as the negatives, the non-relevant images to the query they assign them to the ones that have a very large loss function. And finally, the dimension of the feature vector is 512. And they use mean average precision to compare the results. So in the first experiment, they re-implement the RMAC. And the RMAC, the authors of the paper, train on Paris to test in Oxford, and train in Oxford to test in Paris. So this is why there are no numbers here. And in this paper, they train only landmarks and then test in Oxford and Paris. And well, here C means using the classification laws and R means using the triplets laws. And we can see that improves a lot using the loss function with triplets and also cleaning the dataset. And well, that the re-implementation of RMAC is not as good as the other. And also the region proposals method with only 16 proposals already outperformed the rigid grid, and as more regions, the performance increases. Well, here we can see that also if we increase the number of triplets in the training, the precision increase. And if we increase the number of proposals of the network, the recall also increase, because if we use more regions, we are more probably taking the objects of interest in the image. So here we can see the heat map of the region proposal with the bounding box estimation. We can see that more or less it works. And the comparison with the state of the art, here they win versus all. And using query expansion or extension, they win most of the state of the art. And well, here we can see qualitative the results. The numbers in blue are the order in the ranking from this paper, and in red is the ranking from the RMAC paper. So, well, here in the third row, we can see that maybe they aren't taking into account the context of the image, because here there's a sky and here it has nothing to do with the query image. But well, in general, here it detects the tower, and here, so it's very nice done. And well, the conclusions are that they have proposed an effective and scalable architecture, that it's very efficient because they encode all the images in a forward pass, and then it's very fast to compute all the distances using only a dot product, and that they use, say, a Siamese network with a triplet loss function, and they optimize at the same time the projection of the PCA and the convolutional network weights, and that they demonstrate the benefits of using the region proposal networks to give the regions of interest of the images to the retrieval, to outperform the state of the art of the retrieval task. And well, thank you. If you have any questions.
Okay, thank you very much for that.